So the Battle of Sexes game is played by two players, a couple. Male and female, okay, a husband and wife, a boyfriend and a girlfriend. So they have to decide on what to do for the evening. They have two choices. They can go to a soccer match, or they can go to an opera, okay? The thing is, during the day they're both working, and after day, without going home, without meeting each other, each of them will independently decide on whether to go to the soccer match or the opera, and then hopefully they will meet there, of course, if they have chosen the same thing. The thing is, one of the sides prefers, being together at a soccer match than being together at an opera, and the other one prefers being together at the opera to being together in a soccer match. The worst thing for both of them is being at separate places, okay? So, numerical representation could be something like this. I don't know, well, let me write the symbol. Okay, I don't know, simple game. Okay, I'm not going to tell which side is the male, which side is the female. I'll leave that to you. One of them is player one. We always choose the row players to be player one, always choose the column players to be player two. Okay. Well, this game, we already know when we look at the best responses, I always like to mark them. Those are the best responses of player one. Those are the best responses of player two. So this game, okay, Gamma Battle of the Sexes, has two Nash solutions. Okay. So I'm thinking whether I should write the wrong thing first and then correct it. So every year I get a bunch of students who says the Nash solution is 2, 1, and 1, 2. Okay? Which is not correct. A Nash solution, a solution in general, is a strategy profile. This is not a strategy profile. It's numbers assigned by numeric representations to a strategy profile, okay? So when you're writing the Nash solution, what you should write here is strategy profiles, not the, in quotation, utilities corresponding to those profiles, okay? So the Nash solutions is SSOO. Okay? So we have two Nash solutions and everything is fine. Well, everything is not that fine because you see there's a coordination problem. In games like this, we call these games coordination games. There's two Nash solutions here. But, if I'm player one, okay, and I believe that we're playing this Nash solution, and my wife thinks that we're playing this Nash solution, then what will happen? We'll end up here. Okay? So somehow, we have to coordinate. Okay? But we'll get into those things maybe a little later. Okay? But there's, when you have two Nash solutions like that, they're both Pareto efficient, which is not something that happens very frequently. But then there's the problem of coordinating on the Nash solution. Thomas Schilling has very interesting points on this called focal points. I do recommend that you read about them. But right now, let's skip those. Maybe we'll come back to that. Let's go into the mixed strategy business. So what I would like to do is see if this game has the mixed extension of this game has Nash solutions. Well, we do know that the mixed extension has Nash solutions by the theorem. So what I would like to do is find those Nash solutions of the mixed extension game. Okay? So, how do we do that? So, that's player one. Let me denote the strategies, the mixed strategies of player one with the letter P. So the number PS will denote the probability that player one will choose to go to the soccer match. PQ denote the probability at which player one will go to the opera. And the same for player two, we'll use Q, QS, QO. Oh, yes, thank you. Okay. So by the way, we know that once we know PS, we know what QO is. Once we know QS, we know what QO is. So this is 1 minus QS. This is 1 minus PS. So rather than taking the strategy sets of the mixed strategy sets of players as an ordered pair, let's just take it simple. Let's take delta S1 to be the interval 0, 1, which denotes the probability that player one will go to the soccer match. Okay? The same thing for player two. Okay? One bit of information is enough here. Okay. So, what would you do? How would you find the Nash solutions of this mixed extension game? And we're assuming that these numbers are Bernoulli numbers that come from a Bernoulli utility function. Actually, by the way, in the real battle of the sexes game, the numbers here are not 0, 0. They're different. So this guy obviously, player one obviously likes soccer. So he goes to opera. His mate, his or her mate goes to soccer. So actually this is worse than, they're separated and he's at something that he doesn't enjoy. So the real battle of the sexes game is something like, minus one, but let's keep it this way, okay? So how do we find Nash solutions?
We want to have such probability.
Sorry?
Maybe we want to have such probability that we make the other opponent indifferent.
So why? So your friend is asking, find such probabilities that the other player is indifferent. Indifferent between what and why?
Going to soccer or to opera.
Going to soccer, but under what condition? You mean going to soccer, for sure going to. And why would that work? So we will have a theorem which enables us, but since we don't have the theorem yet, the stuff that you learned in 204, let's do the basic stuff. So if you were given an ordinary game up to this point, how do you find Nash solutions? We use best responses. So let's try finding best responses of the players. Okay. Well, for best response, how do you find best responses? Sorry?
Like the numerical representation.
Use the numeric representation. Find the maximizers of the numerical representations. Okay. So U1 of PS, QS. Again, we don't need PO, QO, because once we know PS, we know what PO is. So what is that number equal to? So 2 times PS, QS. 1 times 1 minus PS, 1 times QS. Thank you. Okay. So, what do I do? PS U1 given QS. So I'm going to draw that function. So by the way, what is that? I'm very good at making arithmetic mistakes. So that's, we have PS QS here, minus minus plus. So 3 PS times QS. And then we have plus 1. And then we have minus PS minus QS. Right? I hope I did not make any mistakes. Okay, so what kind of an animal is this? Or actually, let me write this as 3QS minus 1 times PS plus 1 minus QS. So, what's the maximizer? So by the way, the strategy set is from 0 to 1. And QS is also between 0 and 1. Does anybody have a picture already? First of all, what kind of an animal is this? What kind of a function is this? That's a linear function, so the graph would be a line. So all we need is the slope and the intercept. Actually, in this case, I don't even care about the intercept that much because the slope will tell me what the maximizer is. The slope term is given by 3QS minus 1, right? So what do we see? If QS is equal to 1 over 3, what happens to the slope? It's 0. So if QS is equal to 1 over 3, that's the function. And actually, I can even tell what this point is. That's 1 minus 1 over 3. This corresponds to QS equals to 1 over 3. If QS is less than 1 over 3, then this number is going to be negative. So we'll have a function like this. And then if QS is bigger than 1 over 3, then this number is going to be positive. So maybe we'll have something like this. Okay? So far, so good? By the way, actually, well, it doesn't matter that much. So I have to be careful, maybe, the intersection point, where is it? So actually, let me do it properly. Well, if you do the mathematics, this is what you will get. So, what is B1? The best response of player 1 in the mixed extension game to the strategy QS, QO, but I need only QS is enough, of player 1. Sorry? We have 3 conditions. So let's go with small QS less than 1 over 3. Then we have a negative, so the best response is to play S, to go to the soccer match with probability 0, right? If QS is equal to 1 over 3, then the best response is so any probability is fine. Any probability measure is fine. And if QS is bigger than 1 over 3, then the maximizer is 1. So go to the soccer match with probability. With probability 1. So far, so good. So we're done with player 1. So actually, we can even draw the graph. Actually, I rushed here. It depends on where they intersect, depends on what QS is and where it is. But the exact shape is not important. The message it gives is important. It's positively sloped, maximizer 1, negatively sloped, maximizer 0, slope equal to 0, everything is a maximizer. So when QS is less than 1 over 3, 0 is the best response. When QS is equal to 1 over 3, PS can be anything between 0 and 1, including 0 and 1. And when QS is bigger than 1 over 3, going to the soccer match with probability 1, going to the soccer match for sure, is a best response. So that's the graph of B1 in the mixed extension game. Okay? So far, so good. So then we do the same thing for player 2. So it's going to be the similar because the game is symmetric. What do you mean by a symmetric game?
Like if PS would be less than 1 over 3.
Okay. Well, for this time, let's do the mathematics just for the sake of completeness. So let's write U2 of PSQS. So this time it's going to be 1 times PS times QS plus 2 times 1 minus PS, 1 minus QS. So that's going to be giving us 3 times PSQS, right? And then plus 2 minus 2 PS minus 2 QS, right? So if I factor out, this time I'm going to take QS as variable, so I'm going to factor out QS. That's going to be 3 PS minus 2 minus 2 PS. I don't care about this part much. That's the part that considers me. So this time I'm not going to draw the graph, but if PS is equal to 2 over 3, the best response of player 2 is, and so if PS is equal to 2 over 3, this term is equal to 0. So his utility is the same no matter what QS is. So everything is a best response. So let me mark 2 over 3 here. So that's what we have. Okay. If PS is less than 2 over 3, if PS is less than 2 over 3, then this number is negative, which means that the best response of player 2 is to go to opera for sure. That is set QS equal to 0. So in this region, best response is 0. And when PS is bigger than 2 over 3, best response is to go to the soccer match for sure. Okay, so that's the graph of B2. So, what can we say about the Nash solutions of the mixed extension of the Battle of Sexes game? So we look at where the graphs intersect, not the best responses intersect, they never intersect, but the graphs of the best responses intersect at this point where PS and QS are both equal to 0, which means that they both go to the opera, and this point where PS is equal to 1, QS is equal to 1, which means that they both go to the soccer match for sure. And this point where player 1 goes to the soccer match with probability 2/3, and player 2 goes to the soccer match with probability 1/3. Okay? So far, so good? Any questions? Any questions? So, first, notice this corresponds to OO, so that's 0, and this is the strategy opera. That corresponds to soccer, and that's a mixed strategy. Okay. Yep.
Why does 0, 0 correspond to
Well, so the notation that we used, so where was it? I think I erased it. So when we said, so rather than taking the strategy set as a pair, we took it as a single number, and we interpreted a number in here represents the probability that the player goes to the soccer match. Okay, so the probability that he will go to the soccer match for player 1 will go to the soccer match is 0. So if he will go to the opera for sure. The same thing for player 2. Okay, so that's again why you should always explain what your strategy stands for. Okay, so rather than using pairs, we said let's use a single number, because if I know the first pair, the first number of the pair, I know what the second one. So there's extra redundant information here. That's why we used this simpler domain. But then the number here represented the probability that the player will go to the soccer match. Okay, so far so good? Okay, so that's one way to find the Nash solutions of the mixed extension game, the classic way that we did before. Of course, the problem here is this works fine when each player has 2 strategies, okay? Because it was easy to draw the graphs and all that stuff. So what we need is, we need a more powerful techniques which will help us deal with cases where players have more than 2 strategies, okay? Any questions? So, next lecture we'll see that. But one important observation here now is the Nash solutions, for the Nash solutions of the original game, there were solutions of the mixed extension game which correspond to those Nash. So, for each Nash solution of the original game, there was a corresponding solution of the mixed extension game. Okay? So, in a way, can we always say that the Nash solutions of any game is, I'll use this in quotations, is a subset of the Nash solutions of the mixed extension game? That is Nash solutions, again in quotation, preserved under mixed extension. We hope that is the case You know, when you extend the game, you should preserve what you already. That doesn't happen, well, then, you know, we're kind of troubled. Which game are they playing, the mixed extension or the original game? Okay, that will cause. So next lecture we'll briefly, well, it should be obvious to all of you, we'll briefly talk about this, and then we'll look into other techniques of finding Nash solutions of mixed extension game. That's it. Did everybody sign the attendance sheet? May I have, please?